Welcome back, everybody. We're going to start doing dynamics today. So we'll start putting together a lot of the things that we've been going over. It's kind of nice to get to the dynamics module because it'll bring in the programming, the linear algebra, the prerequisites, all of it comes together and we use all of it. So I'm going to start with one-dimensional dynamics. And I'm going to spend a lot of time harping on a particular kind of dynamics. I'm going to spend a lot of time on this equation, x dot equals alpha x. And you guys will remember that x dot is the same as dx by dt. The dot also means derivative. And I'm going to spend a lot of time on this equation because it turns out that a lot of other, much more complicated dynamics, you can boil them down to this. So if we understand this one really well, it will really help for the other more complicated dynamics. So we're going to spend some time with this. So that's where we're going. But let me start with something else. Let me start describing kind of like the general picture of what we're doing. And the general picture of what we're doing is that you often know the forces on a system as opposed to knowing its time trajectory. So what do I mean by that? Let me describe it. So, for example, if you have a population of bacteria and you want to know what is the population size going to look like as a function of time? Well, imagine that there are bacteria and they're in a plate where you're giving them infinite amount of food, you give them as much food as they can eat, and they're in optimal conditions. Then the reproduction is going to depend on the number of bacteria. So how fast the bacteria are growing depends on the number of bacteria. And you know that. So let's say that x represents the number of bacteria. What you're saying is that you know the rate of change of x as a function of the population size. So we're going to make plots like these where we're plotting dx by dt, the rate of change on the y-axis, and x itself on the horizontal axis. But maybe what you'd really like to know is x of t itself. Maybe you'd like to be able to plot x as a function of t. So maybe we have the thing on the left, but what we want is the thing on the right. And it turns out that there are many situations in biology and physics and so on where that's what we have. Okay, we have this information, the information on the left, not the information on the right. How do we go from the one on the left to the one on the right? There are some cases where if we know the function on the left, we can write down what the function on the right is. And that means that we can solve it analytically, right? It means we can write down a specific function. But it turns out that for many more cases, we can't write down a specific function. And then there are other methods, there are numeric methods to figure out what this plot on the right would look like. And those are the methods that we're going to be focusing on today. We'll do a little bit of analytics, but mostly we're going to be doing the methods for the situation where we can't solve it analytically. They're more general. So I said one of the conditions is, the rate of change of the bacterial population as a function of the population. Another typical example is if you have a network of neurons. So in neuroscience, this is what most comes up. If you have a bunch of neurons and they're connected to each other, and maybe some of these are inhibitory, some of the connections are excitatory. What you know is, let's say that you wrote a vector that represents the firing rate or the activity of each neuron. So this vector would have as many elements as there are a number of neurons. And then what you know is the forces that each neuron is creating on the other neurons. If an excitatory neuron is has a lot of activity and is connected to a second neuron, then that second neuron's activity will tend to grow. If it's an inhibitory neuron, that second neuron, its activity will tend to go down. So actually, you have something that looks very much like the picture that we described for the bacteria, right? We have dr by dt as a function of r. You know the current activity, you know what rate of change of the activity that is creating, but we want r as a function of time. We want to be able to say, what does it look like as a function of time? 2 days from now, what is going to be the activity of these neurons? These are the kinds of things that we're going to solve. So that's the key problem, going from the left to the right. So it turns out that if you have the plot on the left, if you know dx by dt for any value of x, you can figure out how to produce the plot on the right. Okay. So here's a simple example. Suppose that I tell you you're on a track and you're going at 1,000 meters per second. And let's say that you're measuring your position. Okay. And let's say that you're at meter 100 at time t equals 0. And you're moving at 1,000 meters per second. Where are you 1/10 of a second later? Or let's make it 1,000th of a second later, 1 millisecond later. Where are you? You're in meter 100, you're going at 1,000 meters per second, 1 millisecond later, you're at meter 101, right? So what did you do there? What you did was you said, I know my speed, okay? So this is the speed. And you said, if that speed were constant, and I moved a certain amount of time, well, that tells me how much I was displaced. But suppose that I told you that as you moved from meter 100 to 101, suppose that I told you that when you reached meter 100.5, suddenly your speed had dropped to 1 meter per second. So where would you be 1 second after you were at meter 100? Harder to say, right? And what I'm trying to emphasize by that is that we're going to make guesses in terms of time steps. At any given point in time, we're going to say, we know x at some point in time, and then using dx by dt, we're going to guess x at t plus dt, a little time step later. And we want dt to be reasonably small compared to the changes in dx by dt. So for example, if your speed is constant, then dx by dt is not changing very much. I tell you you're going at 1,000 meters per second. After 1 second, yeah, you'll have moved a meter. If dx by dt changes a lot, and I tell you, oh, half a second later, now it's fallen to 0, then you've got to cut your time step down. Right? So for our guesses, our dt has to be small compared to how fast dx by dt changes. So how do we make that guess? Well, what we're going to use is Taylor expansions. So I'm going to remind you guys that we said that any function f of x, so any function f of x, we could write it as f of x naught plus x minus x naught times f prime of x plus a half x minus x naught, the second derivative of x, evaluated at x naught, and so on and so forth. And this was equal to the sum from n equals 0 to infinity of 1 over n factorial x minus x naught to the n times fn evaluated at x naught. So we turn any function into a polynomial. X minus x naught, that's going to be our dt. That's our little step forward. So let's rewrite this in terms of the variables that we're using now. Okay, we're going to write the very same function, But now, instead of f of x, we're going to write x of t. By the way, I'm sorry that I didn't post notes before the lecture, but this thing that I'm writing right now, I'm going to turn it into a PDF and I'm going to post it after the lecture. So again, you're welcome to copy stuff, but you don't really need to. And I now have the recording system down, so the recording is also going to get posted. Okay, so t is going to play the role of x. That's the thing that we're stepping over. That's what we're trying to guess. And x is going to play the role of f in this function that we wrote. So, we could say this is x of t naught plus t minus t naught times x dot evaluated at t naught plus a half t minus t naught x double dot evaluated at, sorry, that's getting hard to read, evaluated at t naught, and so on and so forth. And in fact, this t minus t naught, that is delta t. That's our time step. And we've already used an approximation like this. When we were proving the chain rule and the product rule, we were using an approximation exactly like this. And you guys will remember that the more terms you take, the better your approximation. So in class, we're going to use just the first order approximation. So meaning we're going to take x of t naught and its first derivative. So this is the first order approximation. And using this, as I'll show you in a second, is also known as Euler integration. So we'll use this in class because it's pretty simple, but it's not the best approximation, right? If you took more terms, you'd get a better approximation, you can get better results, more accurate results. So a lot of the machine equivalents, for example, if you're using Julia and you use differential equation solvers rather than writing your own, we're going to write our own using Euler integration. Those differential equation solvers typically use more than the first order approximation. And even if you don't have the second derivative explicitly, you can use estimates of the second derivative to improve the results. So what does improving the results mean? It means that for a certain size of time step, you become more accurate. The smaller the time step, the more accurate, but the more work you have to do because the more time steps you have to compute. And these differential equation solvers, for example, you might hear names like Runge-Kutta or second, third order, they use these higher terms. But the concept of what they do is exactly the same as what we're going to do. We're going to use just the first order term to keep things relatively simple. Okay, so then what we're going to say is x of t is approximately x of t naught plus dt times x dot of t naught. Right? That's the first order approximation. X of t, this is what we know. Right? Remember when I said, oh, we've got a plot where we've got dx of dt as a function of x. So that means that for any value of x, I can tell you what x dot is for that value of x. So we know this term. We know this one right here. dt, we're going to choose. Oops. And we're going to choose this one. And we're going to make it small. What does small mean? That's going to be one of the important questions, right? And then this other one, this is our initial condition. So for example, this might mean that the initial condition was I am at meter 100. And we chose a dt that was 1 second. And we said we're moving at 1,000 meters per second. And then the guess that was made followed exactly this approximation, right? It was 100 plus 1 second times 1,000 meters per second. Sorry, 1 millisecond. We didn't choose 1 second, we chose 1 millisecond. And that's where we got the guess of x of t being equal to 1,001 meters. Okay. And I'm going to rewrite t not as t like that, but I'm going to rewrite it as t plus dt to make it, sorry, t naught plus dt to make it explicit that we started at t naught, we start at some point, and then we're making a guess 1 time step later. And let me rewrite this one as well to make that explicit here as well. X of t naught plus dt. So this is a recipe, essentially. So the Euler recipe that says x of t plus dt is equal to x of t naught plus dt times x dot of t naught, evaluated at t naught. And that recipe we can use over and over and over. So that means, suppose that you start at t naught, and you know what x is at that point in time. You're starting from some point in time. And suppose that you know dx by dt as a function of x. Well, that means that you know all the terms that are here, right? You know this term, that's your starting point. You know this term, that's the one that we chose. We're going to choose dt to be small. And you know this term from knowing dx by dt as a function of x. And so that means that you can guess what x of t naught plus dt is going to be. And once you know x of t naught plus dt, then you can iterate. You can do it again. And that'll give you the guess for x of t naught plus 2 times dt, 2 time steps forward. And once you know that one, you can iterate again. And you're going to have a guess for 3 time steps forward. And you can just keep going. And doing that process, so iterating this recipe, is what's known as numerical integration. And notice that we never wrote down an integral symbol here. Right? We never solved an actual integral. And that's why it's numerical. We're doing it by this approximation rather than solving it analytically. So, so this is what we're going to use to solve equations. And this is what we're going to use especially to solve equations that cannot be solved analytically, which are many of them. And when you're working with neural networks, often that's what you find. So let's do an example. Okay. So the example that I want to do, hang on a second. So I've got some complicated technology to try and make sure that that the recording works while we go across the two, the computer and the iPad. So bear with me for a second. But the example that we're going to do is the following. Suppose that I tell you that x dot of t x dot as a function of x, is 8 times the cosine squared of x plus 2x minus 3.5. And suppose that I tell you that x at t naught is equal to minus 0.65. And I want to plot what's x as a function of t. How is that going to grow? So this is not analytically solvable. Right? There's no simple function that I can write down that will tell me what to plot on this plot. So let's go through using the Euler recipe and using the computer to help us iterate. We could use the Euler recipe by hand. Nothing wrong with that. It would just be a little slow, right? But we can all program. Now we can use the computer to do that for us, and so we can move much faster. So let's do that. And here's where I need to try out the technology. That's kind of fun, isn't it? So, okay. Okay. We can now do this fine. So here's the function that we were talking about. 8 times the cosine of x squared plus 2 times x minus 3.5. And let's plot that. Check that. Yeah, you guys can see all of this. So I'm just going to make an x-axis that runs over, I chose from minus 3 pi to 3 pi, but it's just a range. And I'm just going to plot this over here. And then I'm going to add a vertical black horizontal line at 0 and a vertical line at 0, just so it looks pretty. So let's go through that. So here's the plot. Let me do it again, just so you guys can see it a little bit better. Okay. So that's the function that we're working with, right? And what I want you to notice is that we've got dx by dt as a function of x. And as I said, what we want is x as a function of t. Very important to keep those two plots separate in your mind, right? Sometimes it's easy to get confused between them. So let's use our Euler recipe, because we have all the ingredients that we need. We know what dx by dt is as a function of x. We've been given a particular starting point, so we can run the iteration. And we'll choose a dt, and we'll try to choose a dt that's small enough that things look reasonable. What does that mean? We'll get into that, into how do you make things look reasonable. So what would this look like? So I've got the solution written out a little bit below here, but I'll try to write it out since that since that will make me a little bit slower, and so maybe it'll help people. I'm going to choose a small value of dt. I don't really know if this is small enough, right? It depends on the equation. So typically what you do is you run the iteration, and you see, do I get a smooth result? If I get a smooth looking result out, that looks reasonable. Or another very good thing that you could do is say, I'm going to run with a value of dt, and then I'm going to run again with a value of dt that's half of that. Right? The smaller the better. And if those two look pretty similar, that means that the first one was already kind of small enough that we're getting reasonably accurate results. If you run with a value of dt, you run again with half the value of dt, and you get very different looking things, that means that your original dt was not small enough, and you should keep making it smaller. So we choose a value of dt. We have a function, dx by dt. Let's choose a time axis. We're going to make a plot of x versus t. Right? So we need to choose some time axis over which we're going to plot. I don't know, let's plot the first. Let me see what I did, since when I first did it, it looked reasonable, more or less. So we'll do that. So what I'm writing right now makes a vector t that has time points spaced by dt that runs from 0 to 2. Okay. And let's make a vector that will hold our values of x. And eventually we're going to plot x versus t. So we're going to make a vector of zeros that is the same size as t, right? Because for every time point, there's going to be some value of x. Okay. And let's start with some initial condition. So why do we need the initial condition? Because you remember in that Euler recipe, we're always saying from a starting point plus dt times dx by dt, I guess the next point. So you need a starting point. If you don't have a starting point, you can't do it. So we need to specify a particular starting point. Okay. So here's our starting point, and then you can, but it's part of the problem. So For example, think of a pendulum. If you've got a pendulum, right? So a pendulum you can describe in exactly the same way that I'm describing here. You know the forces. If you tell me the position and the velocity of, say there's a marble at the end of the pendulum, of the marble, I can tell you what's going to happen. But a marble that's hanging down and still, what you predict for the future is very different from a marble that's hanging down and moving, right? Or a marble that's here versus one that's pendulum is here, that's also very different. So if you want to use this process to plot out what the pendulum will do, you have to say where are you starting from. If the problem doesn't tell you which one to pick, then you are going to have to pick
So
one.
in this case, you just picked it.
In this case, I just picked something. So why did I pick minus 0.65? It turns out to be just to the right of this crossing, so it makes kind of like a cute-looking function at the end. But yes, for the illustration purpose, could have picked anything. And of course, with a computer, it's nice that we can just run this and then pick something else and just see what happens, right? Okay, so we're going to run over time. So from the first time step all the way to the last minus 1. And for each time step, we're going to use x at that time step to help us guess what x at the next time step is. Okay? And that's why I'm ending at length of t minus 1, because at that one, we're going to guess what x of the final point of t is. And so the Euler recipe is that x at the next time step is x at the current time step plus, here, let me make this a little smaller for now so you guys can see that, is current time step plus dt times dx by dt, which in this case I've defined as this function here. Okay, so that's where this dx dt came from. So it's dx by dt at the current time step. That's the Euler recipe. That's the first order approximation. Yeah?
What did you do to the minus 1 again? Like t to minus 1?
Oh, because imagine when I is the length of t minus 1, we're going to be guessing what x for the final point is over here. So it's because of this I plus 1 on the left. So in principle, that's the other recipe, relatively simple. We should be able to just run it and now get a plot of x as a function of t. So we could just at first run, oops, I don't know what that character is, never mind. It doesn't crash, always a good sign when your code doesn't crash, right? Now we actually want to plot it and see if it came out nice. So let's just plot and let me put some labels. So this is the plot that we wanted, which is x as a function of t. All right, let's see if we can do that. And let me bring this back so you can see it. So that's what x looks like as a function of t. A completely different function, right? The axes are different. The other one was dx by dt as a function of x. This one is x as a function of t. And you can completely see what the trajectory of x is as a function of time. Now, this thing that we just did, it has a number of properties, the Euler recipe and the numerical integration. And let me come back to the iPad. So we did it for this simple function in which x is a scalar variable. But notice that the function is nonlinear. It's got these cosine terms, cosine squared terms. We're going to be spending a lot of time on linear dynamics, where the function on the right-hand side of the equal sign. So when dx by dt is a linear function of x, this is what is called linear dynamics. But what we were using just now was definitely nonlinear, right? So the Euler recipe doesn't only work for linear dynamics. And in addition, it doesn't only work for scalar dynamics, for one-dimensional dynamics. We could just as well have written as our Euler recipe, we could have written it for a vector. So we could have written the vector x at time t0 plus dt is equal to the vector x at time t0 plus dt times the time derivative of the vector x at t naught. So it's a very general rule. And again, here we could use higher order terms if we wanted to. So we're going to start with linear dynamics, but I want to emphasize that Euler is very general. It covers nonlinear and multidimensional dynamics. Yes?
Are those two terms supposed to be multiplied or added together?
Thank you. So let me try and clarify that. This thing has a plus, and this is dt times dx by dt. Thanks. Okay, so I told you about Euler. We're going to generalize it later. Right now, for today and tomorrow as well, we're mostly going to be talking about linear dynamics. And today, we're going to be talking about one-dimensional dynamics. And in fact, we're going to spend most of it today talking about one-dimensional linear dynamics. Why do we do that? Because so much of the other dynamics ends up being boiled down into that. So it's really important that you guys kind of really get that one, the one-dimensional linear dynamics. If you get that, it will really be the basis for everything else. So one-dimensional linear dynamics. The simplest equation there that we might have is something that looks like x dot is equal to x. So the thing on the right-hand side is linear. The thing that we multiply x by is just 1. And we're not adding anything else to x, so it's very simple. There's no squares or anything, and it's one-dimensional. And this one does have a simple analytical solution. So this is something that we can write. Okay? So remember, what we want is x of t, right? The equation that I wrote down on the left, that's the plot of dx by dt as a function of x. And we want x as a function of t. So how do we get that? What we're saying here is that there's some function of t, x is a function of t, such that when we take its time derivative, so it's x as a function of t, its derivative with respect to t is itself. Right? Because we're saying x dot equals the same thing that we started with. So it's some function whose derivative is itself. We talked about that function 2 days ago. Anybody remember what that function was? Yeah. Say again? E to the x, exactly. The derivative of e to the x with respect to x is e to the x. Okay, so there the variable names are a little different, so let's turn that into this thing, right? Here we wanted a function of t such that its derivative with respect to t was itself. So what would that be? E to the t. Thank you very much. So e to the t is a solution to this equation. What does that mean? That if we take its derivative, d of x of t by dt is d by dt of e to the t, which is e to the t, which is the thing we started with, right? So, great. This is indeed a solution to the equation. Now, there's more solutions to the equation. It's not just this one. Because it turns out that if you multiply e to the t times any constant alpha, what's the derivative of this function? This with respect to t. Thank you for indulging me. I know you know and it looks boring, but I appreciate indulging me on this. Okay, so if you take the derivative of this with respect to t, you get, again, alpha e to the t, which is your x. So this function is also a solution. And in fact, that alpha corresponds, remember that I said, oh, you always need the initial condition? So if we're going to solve this equation numerically, we need to know the initial condition. Well, the same is true for the analytical solution. You know, they go hand in hand. So that alpha is the analytical solution. Sorry, is the initial condition. So what do I mean by that? If we look at this equation, this one right here. What is x of t when t equals 0? Almost there, almost there. You're almost right. So when t equals 0,
Alpha.
exactly. So alpha is the value of x at t equals 0. Right? So we can equally rewrite this as this is x at t equals 0 times e to the t. And here's the explicit description of the initial condition. And that's the solution to x dot equals x. So what does this look like? Let's add one more wrinkle to it. And the one wrinkle that I want to add is, what if we have something that looks like x dot equals alpha times x? So again, we're still doing linear dynamics, so alpha is going to be a constant. So this is, the thing on the right-hand side is still a linear function. What would be the analytical solution to this? Any guesses as to that? So x of t should be a function such that when we take its derivative, we get alpha times the original. Let's try e to the alpha t. So what if x of t equals e to the alpha t? Well then, dx by dt would be equal to alpha times e to the alpha t because of the chain rule. Right? We can make an auxiliary variable y equals alpha t, and it would be e to the y, the derivative of e to the y with respect to y, just itself, and the derivative of y equals alpha t with respect to t. That's what brings down the alpha. And this is equal to alpha x. So that's exactly what we had there. But that was the equation that we started with. So indeed, e to the alpha t is a solution to this equation. And this is the one that everything is going to boil down into. X dot equals alpha x. So this some constant e to the alpha t being the solution. So the thing on the bottom, actually, I'm going to rewrite that. I'm just going to write out the fact that this is the analytical solution. Some constant times e to the alpha t, where k and alpha are constants. Everything is going to boil down into that one. So that one you really want to sear into your heads. So what does this look like? Well, let's plot it out. So, for example, let's say that we have x as a function of t. What would this look like for, actually, sorry, I'm going to rewrite this. Apologies for rewriting. It's x of naught. Because again, that's the value that it takes when t equals 0. When t equals 0, e to the alpha t is 1. So this corresponds to x at time equals 0. So let's plot that out. Let's suppose that alpha were bigger than 0. No, go away. Let's suppose that alpha were bigger than 0, and at t equals 0, we started at some positive x. What would this look like as t grows? So if you plotted this out, if you're just plotting that function, you're plotting, so I've told you that x of naught is positive, and now I'm asking you to plot e to the alpha t for alpha bigger than 0. I'm asking the person in the Princeton cap at the front. Yeah, just roughly. Would it get smaller? Would it get large? Yeah, it would grow exponentially, right? As t gets large and alpha is positive, e to the alpha t is going to get very large. So this is exponential growth. It's going to look like that. What if x of naught, and in fact, it's going to go off to infinity as t goes to infinity. Right? What if x at t equals naught were negative? Then what would it look like? Say that again? Yeah. So can you, I don't know, make a hand gesture to tell me what I should draw. Yeah, it'll be just kind of like the mirror image of that one. So if alpha is bigger than 0, things are going to kind of like move away exponentially, literally exponentially, right? This is an exponential. They're going to move away exponentially from x equals 0. Okay. So this horizontal line right here, this axis is the x equals 0 axis, and you can see that when alpha is bigger than 0, we're moving away from that. And you move away from that exponentially. So how about when alpha is less than 0? What is that going to look like? So let's again start with a couple of x naughts. Actually, I'm going to make my x naughts larger. So we'll do these two examples. And what we're plotting is x of t equals x of naught e to the alpha t. And in this case, alpha is negative. So if alpha is negative, what happens when t is very large? What's alpha t when t is very large? Is it positive or is it negative? Alpha is negative. It's going to be negative, right? When t is very large and positive, if alpha, say, is -1, then alpha t is going to be very large and negative. And so what is e to the alpha t going to be?
0.
It's going to, yeah, it asymptotically approaches 0. In fact, it exponentially approaches 0, literally, because this is an exponential. So this is going to look like this. And it doesn't reach 0 exactly. That should have been symmetric around 0. The two green lines should be mirror images of each other. It will never reach 0 exactly, but it approaches 0 exponentially. Why is that the case? Because e to the minus alpha t is the same as 1 over e to the alpha t. So that means that if alpha is negative over here, if alpha is negative and t is very large, that's like 1 over e to the some large positive number, and so that's going to get very small. So if alpha is negative, you approach 0. You get really close to 0, and you tend to stay close to 0. And so this is going to be the distinction between two fundamental types of points in dynamics. Some are called stable fixed points, and some are called unstable fixed points. Fixed points are points in dynamics where if you're at them, you stay there. And unstable ones have the property that if there's any noise, you move away from them. Where the stable ones have the property that if there's any noise, you move back. And those two, and where those two flavors appear and disappear as you change parameters, those have huge effects on the properties of your system. So these two cases, alpha bigger than 0 and alpha less than 0, they're really, really important to be aware of and understand, kind of like in the terms of what we've been showing right now. So the equation that we had, the one that we started with, was x dot equals alpha x. Right? And that one led to the solution x of t equals x of naught e to the alpha t. So when x equals 0, what's x naught? Sorry, when x equals 0, how much is x dot? If you look at this equation, what does it say? Person with the beard. And when x equals 0, how much is x dot?
How much is x dot?
Yeah.
That's 0.
Yeah, right. If this is 0, then that's going to be 0. And when x dot is 0, how much are you moving? You don't move at all, right? X dot is dx by dt, is your rate of change of x. So when x dot equals 0, that means a value of x where when you reach that, you stay put. That's what's called a fixed point. Okay. The dynamics are such that you don't move at a fixed point. But now imagine that there were a little bit of noise. Okay? So x equals 0 is a fixed point. If you're there, you stay there. But now imagine that there's a little bit of noise. And in real systems, there always is a little bit of noise, even if it's just thermal noise. If there's a little bit of noise, and you move a little bit away from x equals 0, what happens if alpha is negative? What will happen? So if alpha is negative, we're kind of like in the situation that we drew here, right? And we were saying we started at x equals 0, so we started at this fixed point. And now some noise moved us, say it might have moved us to here, or it might have moved us to there. But the dynamics are such that we tend to go back to x equals 0. Okay? So when alpha is negative, if there's some noise, if you're at the fixed point and some noise moves you off the fixed point, you tend to come back. And that's what makes it a stable fixed point. How about when alpha is positive? Suppose you're at x equals 0 and there's a little bit of noise and you move off of x equals 0. What will happen after that? So that's the picture that we drew over here.
We'll just keep on doing it.
Yeah, you'll move away from the fixed point. So when alpha is less than 0, this implies that x equals 0 is an unstable fixed point. And those are kind of key properties to know about. So let me show you some of that. So let's do the case where alpha is bigger than 0. And what I'm going to do is I'm going to put a bunch of dots up. So I'm plotting dx by dt as a function of x. Okay? And that's this green line. So this is the case where alpha is less than 0. Sorry, this is the case where alpha is bigger than 0. That's why the green line slope is positive. And when alpha is bigger than 0, what I'm doing is I'm putting in a dot and I'm just following the dynamics. I'm using that Euler recipe to move it, to animate it. Okay. And for every dot that I put down, I add a little bit of noise at each time step, just to illustrate what happens when there is noise. And you can see that you keep moving away. And I keep adding dots. As they move off the screen, I kind of like add them again near the center of the screen. So again, alpha bigger than 0 means that you move away from the fixed point. And x equals 0 is the fixed point. Right? If you're to the right of it, you move further away to the right. If you're to the left, you move further away to the left. For alpha less than 0, let's see what happens there. For alpha less than 0, then you move in towards it. And it doesn't matter if we add a little bit of noise, you're just going to end up moving back towards the stable fixed point. Okay. So let's do another case. Now let's look at this case. And what we're going to be doing is we're going to be building up more and more complicated dynamics. Right? We started with x dot equals x. Then we went to x dot equals alpha x. Now we're going to add something else. We're going to do x dot equals alpha x plus a constant. So things are a little different. Thank you. So now we're going to x dot is alpha x plus a constant. And tomorrow we're going to build up to multidimensional dynamics. But kind of like this way we go to more and more complicated dynamics until we get to dynamics that can describe, say, biological networks. That's kind of where we're going. So let's again build our plot of x dot equals alpha x plus beta. So in this case, when x equals 0, how much is x dot? Everybody is getting too bored to even answer. Thank you. Thank you. Thank you. Keeps me awake. So beta is just describing the intercept, right? And the slope is alpha. So this point is beta, and this line has slope equal to alpha. And what I want you guys to see is that all we've really done here is we've shifted the line, right? So we had a straight line that crossed 0, and now we've shifted it. And when you have a straight line, shifting it vertically is also like shifting it horizontally a little bit. But what's going to happen to the dynamics around here is the same as what we'd seen before. So when x has this value, when x is right here, that's when dx by dt is going to be 0. Right? So this line, what I plotted here is dx by dt. When that crosses 0, that's the fixed point, because that's the value of x at which dx by dt is 0. When dx by dt is 0, you're not moving. Right? So this is the fixed point. And we can ask, is that fixed point stable or unstable? If it's stable, everything is going to move towards it. If it's unstable, things are going to move away. So how can we tell whether it's stable or unstable? Well, exactly the same as when we had just x dot equals alpha x. Because you can see that if there's some noise that moves you, say, a little bit to the right of the fixed point, you can then ask, what's dx by dt? If you're to the right of the fixed point, dx by dt is positive. Right? So if you're to the right of the fixed point, dx by dt is bigger than 0. And so that means that you're going to be moving further to the right. And if you move further to the right, you then ask, how much is dx by dt? Oh, it's even bigger, and it's also positive. So that means you're going to keep moving even further to the right, and so on and so forth. Whereas what happens if you're to the left of the fixed point, if you're a little bit negative with respect to the fixed point? So say that x has this value. Is dx by dt positive or negative? So I want to remind you that this line, this black line right here, that guy, this is the dx by dt line. So if I'm right here, if this is my value of x, is dx by dt positive or negative? Negative. So which way are you going to be moving? Towards more negative values of x or towards more positive values of x? More negative, right? Because dx by dt is negative. So if you're here, you move that way. If you're here, you move even further that way. And we have exactly the same picture as we had before. So one way to think about that is to say, look, let's change variables to turn this problem into the x dot equals alpha x problem. So let's find, when is it that x dot equals 0? So x dot equals 0 implies that alpha x plus b plus beta equals 0. That means that x equals minus beta over alpha. Okay. And so let's write a new variable, y equals x minus this value that we found right here. So we'll write it as plus beta over alpha. dy by dt, well, if we take the derivative of what's on the right-hand side with respect to t, beta over alpha is a constant. Right? That's just a constant. So the derivative of that goes away. So dy by dt is the same as dx by dt. And dx by dt, we said this is alpha x plus beta. But we know what x is in terms of y. Right? Because y equals x plus beta also means that x equals y minus beta over alpha. So that means that down here we can write this out as alpha times y minus beta over alpha plus beta. Why am I doing that? Because now I've got an equation that's purely in terms of y. Right? So I had a description in terms of x, and now I'm turning it into a description in terms of y. Yes?
Sorry, where did the y come from? I didn't
Oh, so the y came, just wrote the definition of y right there. And how did I choose that y? I chose it as x minus the value of x that would make x dot equal 0. So let's just write this out. So this is equal to alpha times y minus alpha times beta over alpha plus beta, which is equal to alpha y. In other words, exactly the same problem, right? We've turned it into that original x dot equals alpha x problem. Right? We just changed variables to turn it into that. So what was it that we did? What we saw is that graphically it looks exactly the same. Right? All we had to do was change the labels on the x-axis so as to make the fixed point the x equals 0 point. That was what we did. That's how we chose the variable y. And so we did a horizontal shift to move that fixed point to 0, and now we get dy by dt equals alpha y, and that we know how to solve, because you know that that means that y of t is y of naught e to the alpha t, and so on and so forth. We've boiled the more complicated problem, this one, we've boiled this problem down into the simpler problem over here by doing that change of variables. So where does that come up? Well, it comes up, for example, when thinking of membrane potentials. Okay. So you guys already did a little bit of this. So when you're thinking of a membrane potential, and you're looking at the voltage of a membrane on the inside with respect to the voltage on the outside, the pores on the membrane form a little resistance. There's a little resistance to electrical charge moving through that. And the different ions on the inside and the outside can be thought of essentially as forming a battery. So I imagine that all of you guys already saw that. And the lipid membrane also has a capacitance. Okay. So that gives us a differential equation. So let's figure out what that differential equation is. What we're going to use is two things. We're first going to use what's known as Kirchhoff's law. The current going into this node should be the same as the current going out of it. So that means that this current going through the resistor should be the same as the current going through the capacitor. And let me skip through this. I hope that you guys know all this from your basic neuroscience classes. This is where that E comes from. If you have a difference in the concentration of charged ions, that sets up that battery. Okay. So the current through a capacitor is equal to the capacitance times the rate of change of the voltage across the capacitor. So that's from Physics 101. If you don't remember it, or you never saw it, just take my word for it. And the current across a resistor is equal to the voltage across it divided by the resistance. And so what we end up with, if we now use Kirchhoff's law saying, oh, the current IR, the current going into this node should be the same as the current going out of it, that's what we've written down here, we end up with this equation. Over here, V dot is E minus V over RC, and that is exactly the X dot equals alpha X plus beta, right? So alpha X is minus 1 over RC, that's alpha, right? So on the left, V is playing the role of X. So we had X dot on the left, now we've got V dot on the left, and on the right, something is multiplying X, or in other words here, V, that's minus 1 over RC, and we've got this E. That's the beta. That plays the role of beta. But they're the same thing. So we can solve it in exactly the same way. We do that same change of variables. Okay? So here's the change of variables that we're going to use. We choose a u such that when u is 0, its rate of change is 0. And this is the equation that covers how the rate of change of a memory potential changes as a function of time. This is ignoring any inputs such as action potentials or anything that drives the neuron. This is just the neuron at rest. And this is known as the time constant of the neuron. And the thing that I'm really trying to emphasize is that what governs the dynamics of the neuron at rest is our old friend x dot equals alpha x. We just change the variables correctly. That's where we get back to. Okay. Now, I want to show you a much more nonlinear function. So we've been doing just the purely linear function x dot equals alpha x, or x dot equals alpha x plus beta. But now suppose that we have this function, x dot, or in other words, dx by dt, as a function of x, is some crazy stuff that is this green line, which you could actually look at if you want to see what it is. It's cosine of 2x plus 4 times the sine of x times 1.6 plus 3 times the cosine of x plus 2 plus 0.25. I don't know, who cares? It's just something I made up. But some complicated function that doesn't look like x dot equals alpha x on its own. But now I want you to think about what will happen for points that start, for values of x, what are their dynamics going to be? How are they going to change? How are they going to evolve as a function of time? And we can read that off of this graph. Right? So the thing that we're going to do is exactly the same as we did before when we were looking at x dot equals alpha x plus beta and trying to figure out, is it a stable point or an unstable point? For example, I can ask you, wherever x has a value such that dx by dt equals 0, sorry, I'm not going to, the question comes in a second. First, the statement. Wherever x has a value such that dx by dt equals 0, that's a fixed point. By definition, when dx by dt equals 0, that means you're not moving. That's a fixed point. But what we're trying to figure out now is which are the stable points, which are the unstable points, what are the dynamics going to be like. So suppose that I'm at this fixed point, and I move a little bit to the right of it. So I'm a little bit more positive than that value of x. Is dx by dt going to be positive or negative? Just read it off of the graph. Positive. So which way is x going to move? Is it going to move more positive rightwards, or is it going to move more negative leftwards?
Right.
More positive, right? So if you move a little bit to the right of this, you're going to move even further to the right. And then are you going to move further to the right? Yeah, because dx by dt is still positive, right? And are you going to move further to the right now? Sure. How about now? Yep, still goes. dx by dt is still positive. And what happens as you approach this point? Well, as you approach this point, you're approaching another fixed point. Right? But this one, you'll notice this one is stable. Because if you're a little bit to the left of the fixed point, if you're a little bit more negative than the fixed point, dx by dt is positive. So you move towards it. If you're a little bit to the right of the fixed point, dx by dt is negative. And again, you move back towards the fixed point. And the reason that I'm showing you this is just to illustrate that what you're using to decide whether a fixed point is stable or unstable is just the sign of the slope as dx by dt crosses 0. You're using a linear approximation right here to figure out whether the point is stable or unstable. So the slope of dx by dt as it crosses 0, that's what tells you whether a fixed point in 1D dynamics is going to be stable or unstable. And it doesn't matter whether the function is linear or nonlinear. Why doesn't it matter? Because you can always do a Taylor approximation around a fixed point and turn it into linear dynamics around that fixed point. So very close to this fixed point, this looks like a straight line. And this is just like x dot equals alpha x with a positive x. This one looks like a straight line with a negative slope, and that's just like x dot equals alpha x with a negative alpha. Sorry, when I said this one, I meant x dot equals alpha x with a positive alpha. This one, for example, is x dot equals alpha x with a positive alpha, locally, linearly. And this one, x dot equals alpha x, with a negative alpha. Right? It's just the slope of when you cross. So let's just illustrate the dynamics of that. I'm going to do the same trick as I did before. I put up a bunch of points, I add a little bit of noise just to kind of like animate things, and then I let the dynamics run. Each point is following the dynamics that are described there. So what does that look like? Here's the bunch of points. There's the dynamics. And you can see you move away from all the unstable fixed points, and you end up at all the stable fixed points. And the stable fixed points are wherever the slope was negative. So this difference between stable and unstable fixed points, and this idea that if you look at the locally linear dynamics around the fixed point, and what do I mean by locally linear? I mean that you take this green curve and you do a Taylor expansion of it, and you look at the first term, and the first term is a linear function. Right? The Taylor expansion is a polynomial. If you just look at the first term, things are linear. No squareds, just the linear part. And then you've boiled down the dynamics into x dot equals alpha x. That's going to be true in one dimension, and it's going to be true in many dimensions as well. And in many dimensions, the tool that we're going to use to boil things down into one dimension is going to be eigenvalues and eigenvectors. That was a big part of the reason why we taught you guys about those there. Okay, one final note before I let you guys go, which is how about if we have a complex alpha? And we'll find that these show up too. So an alpha with a real part and an imaginary part. Right? So what if we had x dot equals alpha x, but now we know that alpha has both real and imaginary components. Keep calm and carry on. You just do everything as normal. Right? So, sorry, this might be my son's school, so I gotta take this. If I don't come back in 2 minutes, feel free to leave. Turns out I gotta go pick my son up from school, so that's the end of class. See you guys next time.